All right, for this lesson, what we're going to do is it's going to be much shorter than the previous ones because we're only looking at one section out of chapter 3 this week. So the workload should be a little bit lighter as you start preparing for exam 1 next week. What I would highly encourage you to do is make sure that you've watched and understand each of the examples that I've worked out of module 1, module 2, and module 3. That exam is going to cover the material from chapters 1 through 3, and the problems that I have worked and the ones that you have seen on the quizzes should give you a great amount of practice for that upcoming exam next week. So this shows you here, excuse me, a list of the 6 questions that we're going to work through today. Okay, so the first one here, we are looking at exercise out of all of these are coming out of section 3.1. And so this first one is similar, or it is problem number 14, where we're asked to determine what an initial temperature is inside of a room, given some initial starting parameters. So what we'll need to do in this one is we'll need to use Newton's law of cooling. And so Newton's law of cooling is just that T of T is equal to our Ts plus our To minus our T sub S, E raised to the negative KT. Okay, so for this problem, we are given a bit of different information, right? So we have our air temperature is 5 degrees Fahrenheit. We have that information. We're also given that that after 1 minute, the temperature reads 55 degrees. And we're also given after 5 minutes, the temperature reads 30 degrees. Okay. So if we assume that our dt of d of capital T over d of lowercase t is equal to k t minus 5, right? So that our t is equal to 5 plus c to the c times e to the kt, right? And our initial conditions, right? We were given that T of 1 was 55 degrees and T5 is equal to 30 degrees, right? So after 1 minute, it's 55 degrees. After 5 minutes, it's 30 degrees. So we can use our Newton's law of cooling, which is given up there at the beginning. We could rewrite this to be T of T minus Ts is equal to To minus Ts, e to the negative KT, okay? And so at T equals to 1, right, we're going to have 55 minus 5, which is our T naught minus 5, e to the negative K. So this is going to be then that 50 is equal to T naught minus 5 e to the negative K, right? So let's use that as our equation 1. We'll see here in a minute why we are referencing the two. Also, we want to look at T equal to 5, right? So when T is equal to 5, we have 55 minus 30, which is equal to T naught minus 5 e to the negative 5k. That simplifies to 25 T naught minus 5 e to the negative 5k. Let's let that be our second equation we're going to do, because what we really need to do is we want to divide equation 1 and equation 2. So that's going to give me we're going to take our equation 1 Divide that by our equation 2. Okay. When we simplify this, we get 2, right? 50 divided by 25 is 2, is equal to the T naught minus 5 cancel out. And that leaves me with e to the minus k. We're going to move this one up to the top so that e to the minus 5k becomes e to the positive 5k, right? And so when we combine those, we get 2 equals e to the 4k. Okay. So to get rid of that, right, we can take the ln of both sides, right? This then comes into the front. And that's going to give us 4k. I'm just going to put that on the left-hand side is equal to the ln of 2. So our k then is approximately 0.173. That's just dividing both sides by 4. So the ln of 2 divided by 4 gives me approximately 0.173. So now we just need to determine what is our initial temperature. Okay, so initial temp. Okay, so that initial temperature, that is at T0. And we have our, let's just take our Newton's law of cooling formula, plug that right there, and now plug in the data elements that we know. So we do know that TS was 5 plus, we have this 55 minus 5 times E to the 0.173 times 1. Okay. And so this is going to give us 5 plus 50 times 1.188. So that's going to give us an initial temperature of approximately 64.4 degrees Fahrenheit. Okay, for this next problem, we're looking at problem number 16. We have 2 large containers, A and B, of the same size, and they're filled with different fluids. They have different temperatures. One is 0 degrees Celsius, the other is 100 degrees Celsius. We have a small metal bar whose initial temperature is 100 degrees Celsius, and it's lowered into a container. After 1 minute, the temperature of the bar is 90 degrees. So we put it into the first container. After 1 minute, it's lowered the temperature to 90 degrees. After 2 minutes, the bar is removed and instantly transferred to the other container. After 1 minute in the second container, the temperature of the bar raises 10 degrees. How long, measured from the start of the entire process, will it take for that bar to be 99.9 degrees Celsius? Okay. So we have a few things we were given, right? We were given that we have K times T minus TS, okay? And so if we were to integrate both sides of that, we would get the integral dt over, T minus T sub s is equal to K. I'm just going to bring the constant outside, and then we have our dt here, okay? Further simplifying that, we could get the ln of T minus TS is equal to, let me scoot this over just a little, KT plus that constant C. And that is T minus TS is equal to C times E raised to the KT. Okay. So let's look at container 1 or container A. Container A gives us, I'm going to call it 1 just because I'm going to do sub 1 and stuff. So we have dt sub 1. That's just signifying we're looking at our first container. And so we have k sub 1 times t sub 1 minus 0, which is equal to k1 t1. Okay, whose solution then is going to be T1 of T is equal to C1 E to the K1 T. Okay. And since T of 0 for that first container, right? So T sub 1 of 0 is equal to 100 degrees, right? We were given that the initial temperature of that a small metal bar is going to be 100. So we have, because right, that's what we're ultimately trying to determine where we can get that temperature at 99.9. So so now we have that 100 is equal to our C1, and that T sub 1 of T is equal to 100 E to the K1 T. After 1 minute, okay, so after 1 minute, we have that T sub 1 of 1 is equal to 100 E to the K times 1, which is 90 degrees Celsius. That's what we were told, right? After 1 minute, that is 90 degrees. So we get that K1 is equal to the ln of 0.9. Okay, so T sub 1 of T is equal to 100 E to the T times the ln of 0.9. Okay, now looking at this after 2 minutes, right? After 2 minutes, we had T sub 1 after 2 minutes is 100 times E raised to the 2 ln of 0.9. So that's going to be 100 times 0.9 squared. So that is 81 degrees Celsius. Okay. Now let's look at container number 2. In container number 2, so that is dt sub 2 of dt is equal to K2 minus T2 minus 100. That is, again, the initial temperature of our second container. Okay. And so that then gives us that T2 is going to be T2 of T is equal to 100 plus C2E to the K2T. Now, when the metal bar is immersed into in its initial temperature, then T2 at 0 is equal to 81 degrees, right? Because we're taking the bar, remember it says we put the bar into container 1 for a minute, we measure, we put it in after a second minute, and we know that how much we've calculated after the second minute, the temperature of that bar is now 81 degrees. We remove it from the first container and immediately put it into the second container. So the bar's temperature when we initially put it into the second container is where it finished after 2 minutes in the first container. So that's the 81 degrees. for our initial starting temperature for that. Okay, so we have that T sub 2 of 0 is equal to that 100 plus C2 e to the K2 times 0, because we're looking at time equal to 0. And so that's 100 plus C2 plus 81. I mean, not plus, it's equal to 81. Therefore, C2 is equal to negative 19. Okay. So we have that T2 of T is equal to 100 minus 19, because of the negative 19, e to the K2, the 2, T. Okay. So let's go to the next slide, get some more paper. So let me just copy this formula here over to the next page so we can just continue our work. Okay, so we have this T sub 2 of T is equal to 100 minus that 19e to the K2T. And so after 1 minute in the second tank, the temperature of the metal bar is 91 degrees Celsius is what they told us, right? So we know that T2 at 1 minute, after 1 minute, is equal to 100 minus 19e to the K2 of T. And we know that that is equal to 91 degrees Celsius because it gave that to us in the initial problem. So that is e to the K2 is equal to 9 over 19. I mean, yeah, 9 over 19, because we minus 100 from both sides, and then divide by that negative 19. So we have negative 9 divided by negative 19, so it's the positive. So this is K2 is equal to ln of 9 over 19. Really, all we've done here is take the ln of both sides. When we take the ln of both sides, remember, we can bring that into the front. Okay, so this gives us that T2 of T is equal to 100 minus 19e to the T ln of 9 over 19. Okay, so if we set T2 of T equal to 99.9 degrees, right? That's what we're trying to do, and then solve. We can get that we have 100 minus 19 T ln of 9 over 19. And that we want it to equal 99.9 degrees Celsius. Okay. So we can simplify this by moving all our constants to one side, right? Minus 100 from both sides, divide both sides by that negative 19. And we're going to end up with e to the T ln of 9 over 19 is equal to 0.1 over 19. Again, taking the ln of both sides, right? We take that ln of both sides and we end up with e raised to the T ln of 9 over 19 is, sorry, we end up with, we don't need to rewrite all of that. We can just say that our T is equal to ln of 0.1 over 19. We don't want that. We want it there. Divided by the ln of 9 over 19, because, again, remember, all of this can be brought to the front. We want to keep the T by itself, so we're dividing both sides by that ln of 19 to get it moved over to the right-hand side. And this is going to be approximately 7.02. Okay, so thus, from the start of this whole double dipping process, the total time until the bar reaches 99.9 degrees Celsius in that second container then is going to be 9 minute 9.02, right? Because it's 7 7.02 minutes in the second container, plus we have to add 2 minutes from the first container. Right? To get a total of 9.02 minutes. Okay, so 2 minutes in the first container plus 7.02 minutes in the second. Okay. Next problem. This one's a really fun, interesting one. I like when people always say, what are you ever going to use differential equations for, right? And I'm like, well, there's this example where if you have a dead body and some of these initial parameters and conditions, you can actually calculate and figure out how long that body has been dead. And so that's what we're going to look at in this example. And so for this first example, or this example here, we have a dead body was found within a closed room of a house where the temperature was a constant 70 degrees Fahrenheit. At the time of the discovery, the body temperature was 85 degrees Fahrenheit. Okay. So 1 hour later, a second measurement showed that the body's temperature was now 80 degrees Fahrenheit. And we want to assume that the time of death corresponds with time 0, right? So the body died and then what, right? And so now we have we want to know if we assume that the core temperature when the body died was 98.6, we want to determine how many hours have elapsed for us to determine how long that body has been dead. Okay. All right. So in looking at this, we're going to, I'm going to use some coloring this time because I want to kind of help point out to you where we're getting some of the numbers, but some of the things to keep in mind that we are given Newton's law of cooling, right? So I'll write that over here again, just so we have it as a refresher to keep in mind. So we have Newton's law of cooling. And then if we separate out the variables, right, that would be dt over t minus tm equals k of dt. We kind of did this on the other one, taking the integral of each of those. I kind of did this on another slide, but so that gives us ln of t minus tm equals our kt plus c. And so that is T is equal to Tm plus C1 e to the KT, right? So all of that from given that we had Newton's law of cooling. Okay, so the first thing let's look at, let's set T of 0 equal to our T naught, and we find that C1 equals T naught minus Tm, okay? So that is T of T is equal to Tm plus T naught minus Tm e to the KT, okay? All right, some things. We are given that our initial temperature, our T naught, is equal to, that is our core temperature at the time of the death, is going to be 98.6 degrees. Our Tm, right, is the temperature here of 70 degrees Fahrenheit. We have that constant of 70 degrees in that room. Okay. Now we want to let the number of hours that have elapsed before the body was found Okay. So this is number of hours elapsed before the body was found. Okay. And that is going to be T sub n. And so that, well, we're going to let n is the number of hours. I forgot to put the n in there. Okay, so T sub n is going to be this 85 hours, right? The temperature of the body here. So at 85 degrees. Okay. So if I wanted T of n plus 1, right? That is because we took the temperature 1 hour later for a second time, and we got that temperature was 80 degrees. Okay. So now, hopefully all of these colorings helps us to see a little clearer how some of this stuff is determined. So first of all, we'll go back to our blue, and we have Tn, right? T of n is equal to Tm equals T naught, not equals, plus T naught minus Tm times e to the kt. Okay, so we're going to plug in all these numbers that we know. We know that T of n is 85, right? That was our purple stuff. We know that Tm is 70. We know Tm here is 70. We know that T naught was our initial. That is 98.6. Okay, I'm going to scoot this over just a little. Fill in with the blue. We have our equal sign here, our plus sign here. This. And then E, K, and our time T is now we're just using N as our time T. Okay. So this, if we simplify this down, right, simplify as much as we can, we end up getting 28.6 e to the kn is equal to 15. Okay. Now what we want to do is let's do this exact same thing, but instead of for n, we want to do it for n plus 1. Okay. So we're really going to take this same formula here. We're going to copy it, paste it over here. Except instead of doing it for n, we're going to do it for n plus 1. Okay. And so remember our n plus 1, that is 80. The remaining portion, the right-hand side, this is all still the same. So that is all still the same. When we solve this down, we end up with 28.6 e to the kn plus k is equal to, and we end up here with 28.6 e to the kn e to the k equal to 10. Okay. And we can, let's go a different color. Let's go. We'll just do the orange. Hopefully it's not too close. Let's get the lighter one. So we can see that this stuff here is equal to 15. So we can plug that in for this piece here. Not out under that one, but here. Okay. And so that then gives us 15e to the k equals 10. Okay, taking the ln, we'll simplify it, getting our constants. We have e to the k equals 2/3, right? 10 divided by 15. We can take the ln of both sides, bring that k to the front, and that's going to give us that k is equal to ln of 2/3, which is approximately negative 0.4055. Okay. So now if we take our 28.6 e to the negative 0.4055 equal to 15, divide both sides by this 28.6, okay, then that is going to give us e to the negative 0.4055 n, which I forgot the n up here, so put the n, is equal to 15 divided by 28.6, taking the ln of both sides, right? When we take the ln of both sides, we end up with negative 0.4055 n equals ln of 15 divided by 28.6. And so that tells me that n is approximately 1.6 hours. So that body has been dead for about 1.6 hours. Okay. Next problem that we are going to work through is problem number 23. This is one of those where we have a tank and it is a 500 gallon tank with pure water. We have brine containing 2 pounds of salt per gallon, and it's pumped into the tank at a rate of 5 gallons per minute. The well mixed solution is pumped out at the same rate. We want to find what is A of t of pounds of salt in the tank at time t. Okay, so similar to problems that we've worked in previous sections, but we have d of A of dt is equal to our rate in minus that rate out. Okay, so the rate in is going to be the 2 pounds per gallon times 5 gallons per minute. And so that equals 10 pounds per minute. Okay, that's the rate in. Our rate out is going to be A of t per 500 pounds per gallon times that 5 gallons per minute. Okay, so that's going to give me A of t over 100 pounds per minute. Okay. So when I look at dA of dt is equal to 10 pounds per minute minus A of t over 100 pounds per minute. Notice my units are similar. That's going to simplify, let's say d of A over 10 minus A over 100 equals dt. We're just getting, separating our variables. We could take we want to integrate this, right? So we could take the integral of both sides. And this is going to give me ln of 10 minus A over 100 equals that negative 0.01 t plus ln of c. Okay. So now just simplifying this out, we have 10 minus a over 100 is equal to c times e to the negative t over 100. That gives me that a is equal to 1000 minus 100 times c times e to the negative t over 100. Okay, so at time 0 or a naught, we had that is 0, so we can say 0 equals 1000 minus 100 c times e to the 0. Therefore, c equals 10. So our formula would be a of t equals 1000 minus 1000, right? Because 100 times 10 is 1000. E to the negative t over 100 pounds. Okay. All right, this next example, problem number 32. This is, we have a 200 volt electromotive force applied to the RC series circuit, in which the resistance is 1000 ohms and the capacitance is 5 times 10 to the negative 6 farad. We want to find the charge, determine the charge and the current at t equals 0.005 seconds. And then we'll determine the charge as t approaches infinity. Okay. So E of t is equal to R dq dt plus 1 over CQ. Okay. So let's dig through all the things we know. We know that our E of t is equal to 200 volts. We know that our R is equal to 1000 ohms. And we know that C is equal to 5 times 10 to the negative 6 farad. Okay. And we were also given an initial condition, right, of I of 0. Our initial current is equal to 0.4, is what we were given. Okay. So now implementing all of the things that we were given, going back to our initial equation up here. We want to plug in the things that we do know. We know that E of t is 200. We know that R was 1000. Okay, 1000 dq dt plus 1 over 5 times 10 to the negative 6 farad, right? So this is going to simplify to dq dt plus 200q is equal to 1/5. Okay, so that's if we're just simplifying this out. Okay. Now if we want to integrate these, right? So if we integrate, we're going to get q times e to the 200t is equal to 1/5 the integral e to the 200t dt plus a. Okay. And that can simplify once we do the once we do that integration, that is going to give me equals 1/1000 e to the 200t plus a. Okay, so this then is going to, if we consolidate this and we want to just have q of t, this is going to give me q of t equals 1/1000, and we're just moving this portion to the other side. So that is going to be simplified. It will be plus, we divide both sides by e to the 200. It goes away in this 1/1000 term, but we're dividing the a over here by e to the 200. But I'm going to bring it from the denominator up into the numerator. And so that'll give me a e to the negative 200t versus a over e to the positive 200t, right? So I'm just moving that up. And when you move it across between the numerator and denominator, rules of exponents tells us that we just change the sign of the exponent. Okay, so now we can differentiate with respect to t. And so when we do that, we get dq dt is equal to negative 200a times e to the negative 200t. We were given, right? We were given that dq dt is equal to our initial, right? And that our initial was the 0.4a. Okay. So when we have that, we can take 0.4 equals negative 200 a times e to the negative 200 times 0. And so a is equal to negative 2 times 10 to the negative 3. Now, we're going to continue this on the next page, but let's look at this. Let this be equation 1. We're going to bring these over to the next page, okay? This will be equation 1. This here, our QT, this will be the second equation we need to bring to the other page. And finally, we'll bring this to the other page as well as our third equation that we're going to need to look at. Okay. All right. So let's copy, paste. Let's just make it that shade of blue so we can track from one page to the next. Here we need this one. Okay, and finally, third. For the sake of saving some paper, I'm going to just move this up here so that we have a little bit more room. Okay. So what we want to do is we want to substitute, let's substitute number 3, right? So this was equation 3, this was equation 2, and this was equation 1. So let's just substitute equation 3 into equation 2. Okay. So we'll take equation 2, but we're going to scoot this over and substitute this A. We're going to go ahead and substitute in this. Okay. So when we do that, this gives us a fourth equation. We'll let this be now equation number 4. Okay. So we're going to work with all of these things. All right. So at t equal to 0, at t equal to 0.005, right? We have Q of 0.005 is equal to 1 over 1,000 minus 2 times 10 to the negative 3 times e to the negative 200 times 0.005. Okay. I will say this right here is really the same as saying 2 over 1,000. Okay. That all simplifies to 1 minus 2 times e to the negative 1 over 1,000. Okay. So we end up with Q of 0.005 is equal to 2.65 times 10 to the negative 4 as a solution. So that is the solution to one part of the problem that we were asked to look at. Let me just make this a little thicker, and we'll highlight this here. That is one of the solutions that we were asked to do. But we've got a little bit more work to do to calculate down a little more. So for calculating the current at time equal to 0.005, we need to integrate with respect to t, right? So let's integrate number 4, integrate equation number 4 with respect to t. Okay. And we get dq dt is equal to d times 1 over 1,000 minus 2 over 1,000 times e to the negative 200t dt. Okay. And so our I of t is equal to negative 2 over 1,000 times negative 200 e to the negative 200t. And so at t equals 0.005, we end up with I of 0.005 is equal to 0.147 eggs. That is another part that we were asked to determine. Okay, this was a 3-part question. So let's do the last part, right? We wanted to determine when t approaches infinity, right? So as t approaches infinity, we want to know what's the charge. And so the current at time t, we have Q of t is equal to 1 over 1,000 minus 2 over 1,000. E to the negative 200t. Okay. So when we're looking at this as t approaches infinity, that's going to be 1 over 1,000 minus 2 over 1,000 times e to negative 200 times infinity. So e to infinity basically is what that's looking at. That's going to leave us with just 1 over 1,000, or you could write that as 10 to the negative 3. So Q as Q approaches 1 over 1,000 as t approaches infinity. And that is the third part of that question that they were asking us to get at. Okay. For this final problem, this one's a little bit more involved, but it has to do, it's another problem with the electromotive force. And so for this problem, remember that our E of t is equal to L di dt plus R I. Okay, so what we're given for this one, we have I is equal to 20 henries, and our R is 2 ohms. Okay, so we have 2 ohms and then 20 henry. Okay, for that. All right, so to find the current in this LR series, right, circuit, we want to use differential equations governing the behavior of such circuits, which is based on Kirchhoff's voltage law and Ohm's law. So we solve for the first interval. Our first interval is, we'll do in blue. So our first interval, right, is that t between 0 and 20. Okay, so for the first one, we're going to take that's going to give us E of t, that is 120, right? And it is equal to, so the 120 I'm getting from right here, the 120. 120 equals, we'll skip a little space so we could put the 20 for our that di dt plus 2 ohms here for our resistance, and 20 here. Okay. All right, so when we simplify this, when we simplify, we get di dt plus 1 over 10I equals 6. And that is a linear differential equation in standard form. And now we want to find the integrating factor, right? So we want to simplify this to to get to that. And so our linear differential equation in standard form, right, is the dy dx plus p of x y equals q of x, right? And then the integrating factor for that is going to be e raised to the integral of p of t dx. Okay, so our integrating factor, e integral 1/10 dt is equal to e to the t over 10. Okay, so the purple is the standard forms. The orangish color here is us doing the integrating factor for our problem. Okay, we want to multiply our, let's give this here, let's call this equation, let's call this equation number 2, and we'll call this one equation number 1. So if we want to simplify this, we want to multiply our second equation with the integrating factor on both sides. Okay. So I'm going to take my second equation here, and I want to multiply by my, like I said, my integrating factor on both sides. I'm going to just move this 6 out a little bit so I can have some space in there. So my integrating factor is E. Well, I could have left the 6 in there a little more. We're going to multiply that by our integrating factor, E to the 10, T divided by 10 on both sides. And that's going to give me, when we simplify and clean that up, we have D dt times E to the T over 10 I equals 6E to the T over 10. And just as a reminder, we have the UV prime is equal to U prime V plus UV prime. So just our product rule there. Okay. So let's take this equation to the next slide. Because what we want to do is we want to integrate, right? So when we integrate both sides, right? So when we do that here, we have to have that d of t, right? When we do it over here, we have dt plus the c, our constant, right? So when we simplify this out, we have e of t over 10 I equals 6. We're just pulling that 6 outside. We could do that with the constants. E t over 10 d of t plus c. Let's just simplify this for a few steps. This is going to give me then 6 e to the t over, t over 10 divided by 1 over 10 plus that constant is equal to 6 times 1/10 is 60. E to the 10 over 10 plus C. So we get that I of t is equal to 60 plus C e to the negative t over 10. Okay. Now we want to apply that initial condition where it said I of 0 is 0. So if I of 0 is 60 plus CE to the negative 0 over 10, we get 60 plus C. So C is equal to negative 60. So the first thing here is we get I of t equals 60 minus 60 e to the negative t over 10 for that interval from 0 to 20. So this is the first thing that we are looking to solve for here. Okay. Now we want to solve the second interval. Okay. So let's come back over to what we were given here. And our second interval is asking us to look at when t is greater than 20, okay? And so when we do that, our initial or our starting condition is when our E of t is equal to 0, okay? So let's go ahead and we can take this portion of the equation here. Except now instead of the 120, we're going to be at 0, right? So when we simplify this one, we get 20 di dt is equal to negative 2I. So di dt equals negative 1 over 10I. Let me just scoot this over and give us a little bit more room. That can further simplify di equals negative dt over 10. Okay. So we want to integrate both sides like we did on previous ones. So when we integrate both sides, that's going to then give us ln of I is equal to negative t over 10 plus c. So I is equal to e negative t over 10 plus c. So I sub t, or I of t is equal to c e negative t over t. I mean 10, not t. So we want to apply our initial condition of t equal to 20 in both equations. So when we do that, we end up with 60 times 1 minus e to the negative 20 over 10 equals c times e to the negative 20 over 10. That simplifies 60 minus 60 e to the negative 2 is equal to c e to the negative 2. Therefore, our c is equal to 60 e squared minus 60. So our initial condition, or our I of t for this interval t greater than 20 is going to be 60 e squared minus 60 times e to the negative t over 10. And so we would say, so that would be the second solution that we were looking at. And so we could write that into one concise answer by saying that our, let me get this black font, that our I of t is equal to 60 minus 60 e to the negative t over 10 for the interval 0, t between 0 and 20. And then otherwise, it's going to be 60 e to the 2 e squared minus 60 times e to the negative t over 10 for our interval t greater than 20.